Hello everyone, hopefully you can see me. I'm just going to keep flicking back and forth, making sure that everything is coming through, seeing me in the chair. Hopefully my sound is coming through, it's not too loud, not too quiet. What I want you to do is just tell me in the chat if everything is okay. Now I did this a long time ago, that's all of last year, which is, ages ago. If it doesn't work for some reason, it would be good to know that things aren't doing what they should. Sounds good? Excellent. I'm pleased to hear that. Okay. I think my little baby computer's struggling a little bit, but we'll do our best to get through things. What I'm going to do today, just so you know what the timeline is we're going to have a quick rundown of all of the content and all the slides so that hopefully you're feeling comfortable with everything that we've asked of you in science this week. If for whatever reason the stream drops out or things are a little bit choppy, that's okay. There will be a video of this saved and I'll post a link to that in our classroom so you can review it. Reviewing it is optional, it's just there if it helps you. Once again, if you could sign off in the chat just to say that you've attended, I'll mark the roll on Spider and let you all let the team back at school know that you were here and attending. Just a reminder for later on this week, we have a Google Meet. That'll be in our next class slot, which I've immediately forgotten what time that is, which is not ideal. Let me double check. It's tomorrow at 12:35. That'll be period 4 tomorrow in our normal time. That'll only be for about 20 minutes. We'll be doing a bit of a Kahoot. I'll be there to answer any questions, just like today, while we're doing this. So if you have any questions throughout, I'll be flicking back and forth to the chat, looking to see if you've got any questions. Like all things at school, I ask that you keep all the conversation anywhere that you may be having it, whether it's on the chat or in real life, as respectful as possible. So if you've got any questions, sign off, just post them in the chat. All right, let's dive into the content for today. We're in term 1, week 5, looking at the material world. Now, what's our Te Rautaki Te Wiki for this week? Well, here's hoping my little baby computer can survive changing slides. It can. We're going through matter and atoms, isotopes and electrons, the periodic table, and then doing a bit of reflection and revision. So, without further ado, let's dive into it. The first thing that was asked of you is to go through and make sure that you're aware of what you need to do on Google Classroom. You will have seen me make a post as well as Miss McNair put up an assignment. In that assignment, you would have seen that there was a Google form for you to complete. That Google form is a little bit of a short quiz to assess your prior knowledge on the material world. That helps us understand where you're at and what we need to do in terms of teaching you. So if you have some time today and you haven't gone through that, please do. My job is to go and help Miss McNair to process all of that data and make sure all of our Year 9s in different classes, we know how they are starting off, and so we can support you to learn all of the content by the end of this term. All right, you can see the Te Rautaki for this portion of the content, so let's dive into it. First up, what is matter? Matter is anything that has mass and occupies space or has weight, right? And what that means is you have mass, you occupy space, therefore you matter. You are made of matter, therefore you matter. You all matter, team. Matter is like a beautiful little word that encapsulates a whole bunch of complex physical ideas. And we're going to be exploring that further in this topic by looking at the structure of the building blocks of life. That's atoms. And atoms, they're what really matters. So everything is made up of atoms. All matter is made up of atoms. And atoms are made up of 3 subatomic, smaller than an atom, parts. The first part is the proton. It's proton, so it's positive, it has a positive charge, and it has some weight. We find our protons in the center of our atom, which we call the nucleus. Now, orbiting around the outside of these protons, which have a positive charge, we have these negatively charged particles we call electrons. Now, electrons don't have a mass. They're very, very light. So we think of them as not weighing as much, as not having as much mass as something like a proton. They orbit really, really quickly around the outside, part of what relates to us having electricity, which we'll learn about at a later stage. The third subatomic particle we need to know has no charge. It's neutrally charged. It's called a neutron. Now, neutrons and protons both have weight, while electrons weigh very little, or both have mass would be a better way to say that. We find our protons and our neutrons in the nucleus of the atom, and we find our electrons hanging out in little rings, which we call shells, right? We call them shells because atoms aren't flat, right? They form a space, and you can imagine like a little Easter egg, you know, the hollow ones that you get that you think are really, really big, and then you open them up on the inside and there's no chocolate in them at all, which is always really disappointing. So those are shells, right? And those shells are where we find our electrons. All right. How do we organize all of our atoms? Well, that's a good question. Thank you for asking it. Our atoms, kia ora, Nishita, I can see everyone's joined. Excellent. Okay, our atoms are organized into this beautiful little grid designed by a chemist a very long time ago, which we should do a history lesson on him. It's a great little story there. But we call this the periodic table, and it's the periodic table because it's made up of different periods, and it's also and we'll break down exactly how to read the periodic table later in the lesson today. We count our different atoms, and we give our different atoms different names based on how many protons they have. If it has one proton, we call that hydrogen, and we give that all of those various atoms of different types, we call those elements. So all the atoms with one proton, we give the name, it's the element we call hydrogen. All the atoms with two protons are the element helium. You get the idea. Those tick up gradually over time, and you can see that we've got a whole bunch of them here, including a whole bunch way down here in sort of these like very high numbers, 113, 114, which if they exist, they only exist for very short amounts of time before disintegrating into some of these other elements here, as well as other subatomic particles. So anyway, here we go. Next bit, elements and compounds. Some of you might know or have heard of compounds. Compounds are what we get when we mix different atoms together. And there are three definitions you need to know here. So the first thing is, we've talked about atoms, right? An atom might be an example like helium, which just sits on its own. One atom with some subatomic particles hanging out on its own. However, when you get two atoms together, sometimes they bond, they join together. For example, hydrogen, if you get a whole bunch of hydrogen atoms together, hydrogen is much happier, much more relaxed, much more stable, would be a better chemistry term, in pairs. So two atoms of hydrogen will bond together, right? Now, it's not one atom, it is more than one atom. We'd call that an element, or we'd call that elemental hydrogen. However, because you've got multiple atoms joining together, we call that a molecule. Any material which contains multiple atoms chemically bonded together is a molecule, right? Now, some molecules are what we call compounds. Now, compounds are where your atoms that are bonded together are two different kinds of atoms, two different elements, right? So, for example, water, the chemical name is H2O, meaning two hydrogens and one oxygen. That oxygen is bonded to a hydrogen here and a hydrogen there. Now, that compound there is also a molecule, but not all molecules are compounds, right? Our oxygen gas, for example, shown in that diagram there, has two of the same atom. So it's not a compound. It's not a joining of two different atoms. It's a joining of two of the same atom. That's the difference. We need to know the difference between elements, molecules, and compounds. Now, in your assignment, what you've been given is some little parts of the atom to label. Now, hopefully, from the information I've just given you, you can label this negatively charged particle here, this positively charged particle here, the neutrally charged green particle there, what these particular ring or shells are, and what we call this group in the center. Hopefully you can figure that out from the information that's there. If you have any questions about that, you can sign them off in the chat, or alternatively, we'll go through it when we do our Google Meet and Kahoot tomorrow. Now, your stirf and saw tasks or exercises are to either label water, hydrogen gas, and helium as either elements, compounds, or molecules. Here's a hint. They might be more than one. Some of them might be both an element and a molecule, right? See if you can figure out which one is which. The key thing, though, is explaining why you've chosen those labels, right? We want to see your thinking, see that you understand those distinctions that we talk about there. Now, you'll see some of the slides that we've got are in yellow. Now, yellow slides are there to let you know that we've given you an opportunity for extension. By the way, if you've got any questions, you can just sign them off in the chat. I'll go through that for you. Hopefully, okay, I'm just looking through the chat. It's a bit choppy. Hopefully we can go through okay. Sorry about that if that is the case. My little baby computer's doing its best to process everything. What I can see, to answer your question, William, so if you go through the week 4 slides, that'll probably be a helpful introduction to going into week 5. With the week 5 stuff, the goal for your work is to go through that content as best you can, and then that should be reasonably good for you. Now, I'm hoping that things are coming back. I'm still getting a message telling me that my stream status is poor, which is not ideal. Can you just sign off in the chat if things are going okay? Okay. I'll go back to the slides. Hopefully that will help. Okay, so you can see these slides here, let me point this way, are yellow. Yellow slides are extra for experts. You don't have to do them, but if you would like some extra things to look at, these might be really helpful for you. This is a little task on scale of the universe, aiming to, I guess, let you have a little bit of a look at just how small atoms really are. You can also scale it up to see the whole scale of the entire universe, and see how big just some of the things that we'll be looking at in term 4 when we tackle Earth and space science. Okay, let's move quickly on to lesson 2 because I don't want to keep you here for too long. Okay, lesson 2, understanding the definitions of isotopes. So, little mahia for you there. Out of the following, list, explain which are compounds, which are elements, and which are molecules. So hopefully based on that information we went through yesterday, you can figure out, there's the answer for you, that nitrogen gas and oxygen gas are both examples of elements. They contain one type of atom, right? While CO2 is a compound, carbon dioxide is a compound. It contains carbon and oxygen. We call it carbon dioxide because there are 2 oxygens, and di in Latin means 2. And now all of these are molecules because they all contain more than one atom. If you could do that without me giving you the answer, then kapai, you're on the right track. What we're diving into now is isotopes, right? Isotopes. Lovely new word. Hopefully it's all going okay. Can you just sign off in the chat if it's still working, you're still getting a signal? Okay. Yeah, so isotopes. What are isotopes? Good question. Isotopes are different, or so you can have the same atom but a different number of neutrons. We call those different forms isotopes. An example of this would be carbon. Now carbon has 6 protons. Any atom that has 6 protons, we give the name carbon, right? Because all of our 6 proton atoms all share pretty similar properties. However, they have slightly different properties, like slightly different, if they weigh more or less, and that can be affected by how many neutrons they have. Now, carbon 12 has 6 neutrons, carbon 13 has 7 neutrons, while carbon 14 has 8 neutrons, right? And those existing in different amounts in the world can be used by chemists and by, some of you might know of carbon dating. That uses this technique. It uses isotopes of carbon to be able to understand this stuff. So really interesting thing there. Key thing for you to know is they're all carbon because they all have 6 protons, but we call them different isotopes, right? Carbon 12, carbon 13, carbon 14, based on the number of neutrons they have. And that introduces us to the concept of atomic weight. Now, atomic weight, if you're looking at a periodic table, you might see that there's a number on the bottom below the element's name and the element's symbol. You often see the atomic number above the element symbol, either at the top there or on the left at the top. The atomic weight is the average, how heavy on average an atom is. Now, you just learned about isotopes, right? You'll notice that, some of them, for example, in carbon can be carbon 13, some of them can be carbon 12. If we take the average overall, you get the average weight of all of the atoms that exist in the universe. So, isotopes and atomic weight. Each proton and neutron has what we call an atomic mass of 1. Now, we don't use kilograms here, because if we did, be way too small. We'd be writing too many zeros. So what we do is a conversion. Just like people convert Fahrenheit to Celsius, here we convert kilograms to atomic mass units, right? And the weight of a single proton, we give 1. The weight of a neutron is also 1. They weigh the same amount, or approximately the same amount. If we were to write that in kilograms, you can see that's 1.6605 times 10 to the negative 27 kilograms. A lot of zeros to be writing there, not something we want to be doing all the time. Now, most hydrogen in the world is hydrogen 1, i.e. it has 1 proton with a weight of 1. Very good. And has no neutrons, hence why it weighs 1, and we give it the name hydrogen 1. You get the idea. Sometimes we have hydrogen 2. Sometimes we have hydrogen 3. Hydrogen 2 has a mass of 2 because it has 1 proton and 1 neutron, and 1 plus 1 is 2. Excellent. Same with tritium. 1 proton makes it a hydrogen. 2 neutrons. 1 plus 2 is 3. It weighs 3. They have special names because we use them a lot in a variety of applications, including if you want to look at the spin of atoms, which is something pretty neat, used in some specialist science, particularly in nuclear science, which is quite cool. So that hopefully should give you an understanding of why that number isn't a rounded, easy to understand number. Now, for lesson 2, a couple of little challenges for you here relating to that slide called atomic weight. Boron has an atomic symbol. Which one is it? Right? Boron has an atomic number. Which one is it? I'll give you a hint. This means boron has how many protons? We call all atoms with this number of protons boron. I think you'll be able to get it. Now, here's a little question for you here. 92.4% of lithium atoms are the isotope lithium-7. That's just an interesting fact. The remainder is mostly lithium-6. Explain why this means the atomic mass of lithium is 6.941. Now, you do not have to do calculations here. The key thing you have to be able to specify is that the number is slightly less than 7. Now, most of the lithium-7 in the world is lithium-7 because most lithium has 3 protons and 4 neutrons. A very small amount, i.e. less than 10%, is lithium-6. that has 3 protons and 3 neutrons, right? Those lithium atoms have an atomic mass of 6, while the other ones have 7. Now, because most of the world's lithium weighs 7, a little bit weighs 6, that is why the atomic mass of lithium is a little bit less than 7. That's the sort of answer we're looking for you there, showing your understanding. Again, another extra for experts little video there if you want to have a look at that. Beautiful video presented by Sir Martin Polyakov, who's an amazing chemistry professor. He has all these videos where he does amazing chemistry, and he talks about those different atoms and elements, and it's so good. If you're interested in chemistry, highly recommend checking it out. Okay, I'm going to quick another check of the chat, make sure everything is okay, everyone is hunky-dory. I'm hoping that everything is going okay. It looks like you all are doing okay. I'm sorry if it's been a bit slow. My little computer's doing its darndest. If you've got any questions, please sign off in the chat. I'll do my best to flick over and answer. Okay. Alrighty. This is our last chunk of content. So if you've gotten through this so far, well done. You can see here another little mahia to test yourself out. How many neutrons, protons, and electrons does the average fluorine atom have? Well, we know from its atomic number 9, right? That means it has 9 protons. Excellent. Now we know that the number of electrons has to be the same as the number of protons. So it should also have 9 electrons. Very good. We've done those first 2 bits. The third bit, which is the hardest bit, is we know that the total weight of the atom is just under, on average, 19, right? So if we look at most of the fluorine atoms will weigh 19. Some will weigh 18, some might weigh less. Most will weigh 19. If we look at that weight of 19, 9 of that weight comes from the protons, right? The remainder comes from the neutrons. How many neutrons do we have? 19 minus 9 is 10. So, on average, a fluorine atom will have 9 protons, 9 electrons, and 10 neutrons, right? Some, a small amount, might have less than that in terms of neutrons, maybe 9 neutrons. In which case, we'd call that fluorine 18 as opposed to fluorine 19. You get the idea. Excellent. Okay, let's dive into the last chunk of content. So, first things first, how to draw an atom. Boy, oh boy. Now, the nucleus is where we put all the protons and neutrons. When we're drawing an atom, and we've figured out how many of each are in there, we draw all of them in the center. The atom that you're looking at here is calcium. It has 20 protons, and I believe it also has 20 neutrons on average as well. So we put 20 protons and 20 neutrons in the center, in the nucleus, the center of the atom. Now around that we have to draw some shells, and this can be a little bit complex because not all shells are made alike. The first shell can hold 2 electrons. The second shell can hold 8, as can the third shell. When we get to the fourth shell, it holds 2 again. Once you get above this, it starts getting a little bit complicated. We start to really talk about that when you get to year 12 chemistry. Maybe a little bit in year 11, but mostly in year 12 chemistry. So you've got a little bit of time to look forward to that, but you're welcome to dive into that content looking at some extension material if you'd like to. The key thing to recognize is that when we're adding in, when we're adding in our electrons, you must fill the lowest shell first. So we draw in our first shell, right? We know we've got 20 electrons to put in for this calcium atom. We put our first 2 in the shell, and then we go, okay, we need another shell. Let's put in our next 8. 1, 2, 3, 4, 5, 6, 7, 8. Very good. That gives us 10 in total. We then need to draw a third shell. Our third shell can hold up to 8. So we put another 8 in there. Now we have 18 electrons in our 3 shells. We still have how many left? 2. Excellent. We've got 2 electrons left to put in. So we draw our final shell and we put those 2 in. Now you only need to be able to draw the first 20 atoms. So if you want to do some practice, we'll spend some time later on in the year, or later on in the term, going through this, but if you want to do some practice, that would be a little good thing to look at, right? Hopefully that makes sense. This next bit is how to read the periodic table. We've already kind of gone through this, but if you wanted some practice on this, remember the atomic number is that number in the top or in the left, right? And that's the number of protons. It also tells us the number of electrons. We've got the element symbol, which is a letter, and the element's name. Now sometimes the element symbol and the element's name will be a little bit different. That's often to do with the original name, either in, say, Greek or Latin, or whoever got lucky enough to name it first. They get to pick the element symbol, and then we give it its English name below. So sometimes it doesn't always line up in a way that we'd like it to, but there's a linguistic reason for that. Below that number is the atomic weight, and that's the average number of protons plus the number of neutrons. It will try and give it to you in a simplified way in a testing situation, so we'll round it up, right? And that'll tell you, on average, how many protons are in an atom and how many neutrons are in an atom. Very good. Okay, last two things, and then we'll leave for you for today. We're looking at rows and periods. So this is how to read a periodic table. So you'll notice that the way that the periodic table is structured is kind of funky, and that's to do with what we just talked about in terms of the number of electrons that can exist in each shell. You'll notice that there's only 2 elements in that first row of the periodic table, or the first period, as we like to call it, right? And that's because in the first period, in the first shell the first electron shell, you can only hold 2 electrons. So we have hydrogen and then we have helium. The next shell can hold how many? 8. Very good. So 8 electrons, so there are 8 spots on our next period. Same with the third shell, and then the fourth shell, it starts to get a little bit tricky. But you get the idea that each layer corresponds, each period corresponds with the number of electrons in the shell, at least up until we get to the 21st elements, which is all we need to know at this stage. You can see here potassium and calcium, right? Potassium and calcium are in the same period. They're down here. That's because they have the same number of electron shells, right? Both have 4 shells. Both appear in the 4th period. Very good. Now, columns and groups. This is the columns or groups is the other way to read it, right? The vertically. Now, what this refers to is the electrons in the farthest outermost shell. And we call the farthest, most outermost shell valence, right? So that we don't have to, get all confused with what we mean by outer, right? So we give it the word valence. And the valence shell is the further outmost shell, and the electrons in it are called valence electrons, right? Now, the number of electrons that are in the valence shell determines what group, right, or what column that element is in. So group 1 elements have 1 electron in their valence shell. Let's have a look at this atom here. It has 2 electrons. This is calcium again. 2 electrons, therefore it is in group 2. And if we were to look on our periodic tables, I don't know if you've got one handy, I always like to keep one above my bed when I'm studying. It's really important to have one as easily to hand as possible. You don't have to have one easily accessible, but you can Google it. You'll find that calcium is located here in group 2 and in period 4. Same for our group 8 electrons, right? Our group 8s all have 8 in their outermost shell, except for helium, which has a full outer shell anyway, right? So it's full, but it only has 2 electrons. But the key thing is, if it's in group 8, it's got a full valence shell. That's the key thing for you to understand. Now you've got 2 exercises here to follow up on this. You want to name the element symbol, element name, atomic number, and atomic weight of that atom, which you should be able to do based on the knowledge you've got. Now, beryllium and magnesium are in the same column or group of the periodic table. What we want you to do is compare and contrast them. You might notice, for example, the number of valence electrons they have and be able to link that to the fact that they're in the same column or group. You might notice that they have a different number of shells, which might tell you then what period they're in. You're welcome to Google these atoms to find out more. If you want some additional fun, you can have a little bit of a look at these periodic tables online, which are nice and interactive. You can look at what temperatures these elements transition from solid to liquid in. It's quite a lot of fun. If you're a little bit bored and you want some extension, I highly recommend spending some time on this. Now, our last lesson for today, we will be completing with you in person in our Google Meet. We'll do a bit of a Kahoot, but the last thing I want you to look at is the huri-tau, which is the reflection task for this week. If you can answer these 4 questions, then you've clearly understood all of the content for this week. If you need to make additional slides or make copies in order to write your answers as long as you want them to, that's all good. Now, that brings us pretty much to a close for the lesson for today. Before we end though, I want you to post any comments that you might have in the chat. I'll just check that there's no one that's really stressed about something, really nervous. See lots of emojis, which probably means that we're happy, which is good, you know, because I want you to be happy. But if you've got any questions or concerns, you're welcome to leave a little bit of a comment. Other than that, that's been us for today. I hope you all are having an okay time in lockdown, that you're looking after yourselves and your families, that you're staying safe. And I look forward to seeing all of you tomorrow in our Google Meet. And with that, that's been us for today. Have a lovely rest of your day.